All right, so this is just a brief introduction of Cramer's rule. A little bit of theory heavy and then the applications. You've probably seen this in algebra 2 and a little bit of pre-cal. Depends on your professor how it's going to it. But we'll get into the basics of what it is, but what the main focus of Cramer's rule actually is. So we're going back to ax equals b. So we're going to solve for the vector x, but we're going to solve it in a unique way. Okay. So a lot of these theorems and lemmas come into Cramer's rule itself, but the biggest one is this lemma here, is given any matrix A, presuming more an n by n matrix, and let B be any vector in Rn, so some arbitrary vector. Okay. So for each of these vectors V's, I can rewrite some matrix B that's also n by m in this format, where it's basically all these vectors except for one. That one is replaced by this vector b. Okay? So kind of like this. And therefore, it also solves for a system of equations in this particular format, right? Just by that portion. So it's so precise that it actually looks like this. So the determinants of each individual case times its individual vector gives you that, which is pretty crazy. So the determinant of B is the determinant of A originally times that x component, or the x1 vector itself, which is pretty nice, right? And this is actually going to comply to Cramer's rule. So the next couple of actually promote from singular to non-singular to comes to a matrix determinant. So if a matrix A is singular, therefore the determinant is 0. So it means the opposite. If the determinant is not 0 or non-singular, it's not 0. Hence these two theorems come into play. But this one is more important because if it's non-singular, therefore there's an alternative to find the determinant of an inverse, which actually is really nice. So if you just want to find the determinant of the inverse of a matrix, it's 1 over the original determinant. Again, if it's non-singular. Okay. Now, the first one, the minimal theorem, just goes into applies with matrices. So again, given two matrices, the determinant of the multiplication of them both is, the nice thing is, the multiplication of each individual determinant together, which is pretty nice because it's kind of like a chain. So if I have C in here, it just tacks on with a chain of multiplication, multiplication, multiplication. But the main focus is actually this lemma and this theorem create Cramer's rule. Because Cramer's rule says basically this lemma at the very beginning, the exact same lemma. So therefore, each component xi is actually equal to the division of the determinants, which is exactly what happens here, because if I divide by the determinant of A, that gives me exactly Cramer's rule. Okay. And this one comes into play later on, but mostly it's going to be those two, which is a real fun one. Okay. So again, this is an alternative of finding the components of x, y, z, or just x, y, just not, instead of just using row reduction and all that. So, just a quick little format you probably learned in algebra 2 or college algebra going forward, and a little bit of pre-cal as well. So how does this work out? So using this formatted of actually, matrix format, we have the basic one, which is A. So A is going to be the matrix n by n, so it's a 2 by 2 matrix of just the components. So 3, 5, 2, and 4. Okay. Now, how does the B's line up? So again, if you've seen this in algebra and so forth, you kind of already know. Usually known as B1, 2, and 3, or C, D, and so forth. It shows that, that column is replaced by its predecessor. So in this case, this one is always going to be our vector B. So that replaces each individual component. So if it's B1, it replaces the first column with just 4, 6. And the next ones are the same. And therefore B2, that means column 2 is going to be replaced with 4 and 6. So this one stays the same as 3, 5, but this one now becomes 4, 6. Just like that. And now we just find the determinant of each individual case. So the determinant of A, again, it's just a 2 by 2 matrix, right? This times this minus that times that. So it gives you 12 minus 10 gives you 2. And we find the determinant of the other B matrices as well. So this one, that times that minus that times that. So 16 minus 12 gives you 4. And then finally, the determinant of B2. So that times that minus that. So 18 minus 20, so it gives you negative 2. So that means x1 is going to be, well, this determinant divided by this determinant. So if I go over here, it's going to be 4 divided by 2. And x2 is going to be this determinant by that determinant. So if I go over here, negative 2 divided by, negative 2 divided by 2. So x1 is equal to 2, and x2 is equal to negative 1. It's a nice little format how that's going to go into play. And it gets much easier when you have to do larger matrices and larger solving for systems. So, for instance, now let's go to a 3 system, x1, x2, and x3. So in this case, our A is going to be 1, 1, 1, negative 1, 1, 2, 1, negative 2, 1. And now we're going to have B1, 2, and 3 because we have 3 vectors, or 3 values we need to find. So in this case, again, remember this is going to be our B. So this just places the first column, and everything else stays the same. So now this time, second column changes. Everything else stays the same. So this is now going to be 0, 1, 6. And the other one is so. And then finally the third one. And again, find the determinant of each one individually. So determinant of A, you could do it multiple ways. You could just, so at this point, when it comes to the class, you could do however you want, right? You could do it the old-fashioned way, break it down into 3 parts, and then find the determinant of cross-product and multiply. You can do row echelon to just reduce it to eventually get you the process. But in either case, you'll get these as your determinants. And now finally we can find x1, x2, and x3. So x1 is going to be this determinant, which is 9 over 9. And they're all over 9 because matrix A is 9. So B2 is 18 over 9. And then finally this one is 9 under 9. So simplified version, we get that. So Cramer rule is really nice. Something nice to finish up the chapter going forward.